Swayam Prabha. Digital India. Educated India.
Okay, hello students. So today I will teach you another very important topic for the point of care biosensors. This is a fundamental concept, that is a strategy of electrochemical detections and tuning. Means definitely we need the high electrocatalytic activity to get the higher signal to background ratio that I already taught you. But before that, we can modify the surface of some different way, not only by nanomaterial, also we can tune by some different way. Let's teach you all the possibilities how we can tune the electrocatalytic activity of the sensor surface that you can use for biosensing applications. So let's come that topic. So today mainly I will cover a enhancement of the electrocatalytic activities and use this enhancement for biosensing applications. So this is the main topic I will cover today. So main keywords for today's topic is the electrocatalytic activities, and these electrocatalytic activities how we can tune. So we can enhance the catalytic activity, or if we need we can maybe decrease the electrocatalytic activity of the surface. As I mentioned, sometimes we may need very high enhancement because we need the high catalytic activity, because this can improve the signal. But sometimes if it is so high catalytic activity, then there may be some other background reactions, side reactions that can increase the background current. So the signal to background ratio can be decreased then. So in this case we have to modify the actual signal, actual activity of the electrode surface. So that is called the tuning, how we can tune the catalytic activity. So let's come this topic. So first is the strategy. So you can see in this slide that so this is just a cyclic voltammogram on the electrode surface. So suppose your electrode surface is nanomaterial coated, and you know this is a potential window. Generally, as I mentioned, the negative is the left side and positive is the right side. And this, if you say this central is the 0. And this cyclic voltammogram, generally you are very much familiar with this kind of cyclic voltammogram, right? Like oxidations and then reductions, right? But in this case, you can see only we are getting the oxidations current. So sometime you may see this kind of cyclic voltammogram also. So slowly you will be familiar. Means in this case there is no reductions peak, right? There is no reductions peak in this case. Only we are getting the oxidations, because it is kind of irreversible reactions. It can be oxidized, it cannot reduce back. For example, the glucose. If you oxidize the glucose on electrode surface, it will be oxidized. Then it will not go back again with the glucose. That's why you will not get the reduction current. It is kind of irreversible reactions. Or hydrogen peroxide oxidations, if you oxidize it. So this is kind of irreversible. But in the case of if you see Fe2, Fe3, these conversions, if you think conversion, so these are the reversible process. That's why you are getting the oxidation peak and reduction peak. Okay, so slowly you will be familiar. So this is one kind of cyclic voltammogram, this is another kind of cyclic voltammogram. See, so in this cyclic voltammogram, you see that the oxidations, only oxidations peak we are getting. So in this case they are oxidizing in the negative region. It means we need low potential and low energy. So easily we can oxidize them, right? So on the electrode surface, this substrate can be oxidized easily. So we can say, based on this cyclic voltammogram positions and peak current, you can see the very high, high current also compared to other cyclic voltammogram that I am going to show you. So I can show you the another cyclic voltammogram. See, In this case, this cyclic voltammogram, it is its peak positions, it is very positive side, right, this side, and current also low. It means your electrode surface in this case is differently active and this case is differently active. So, this case it is highly active, this is case it is highly active, and in this case it is low, it is low catalytically active. This is highly active or highly catalytically. I mean, this is which catalytic? You have to mention electrocatalytic. Electrocatalytically this one active, because we are measuring the electrochemical behavior. So, what is the main thing you are learning in this slide? That to understand the electrocatalytic behavior of your electrode surface, so you can run a cyclic voltammetry, this kind of irreversible behavior generally showing this kind of things you can measure on your electrode surface. Means if you are getting your oxidation peak in the low potential region and high current, so it means your surface is highly electrocatalytically active, and if you are getting the higher potential, you need more potential to oxidize it, so it is low electrocatalytically active. Now see, sometime you may need your surface highly electrocatalytic active, sometime you may need low electrocatalytic active, sometime you may need in between. So why I am telling you sometime you may need high, sometime low, that I mentioned, right? It's depend on your signal to background. This is very important parameter you have to keep in mind. See, your background should be very low, and S should be very high. This is signal, should be very high, so that your signal to background ratio will be very high. So, to decrease other side reaction like oxygen side reactions, because in your dissolves, when you are measuring the cyclic voltammogram, so your solutions may contain the dissolved oxygen, right. If it is the real sample, then it may contain some other interfering species like ascorbic acid, right, uric acid, so or glucose or some fructose, means some other things present, they can be oxidized. So, if your surface is very highly catalytically active, they can show their contribution. So, background can be increased, that is why we have to tune the activity. Okay. So, if it is so low, then your signal also will be very low, means if your catalytic activity is very low, like it is showing in this region. So, in this case signal also will be background low and signal also will be very low, signal to background ratio will not that much high. So, you need to improve then. So, how you can improve? Maybe you need to enhance the catalytic activity some different way, that I am going to teach you how we can improve the catalytic activity. So, if you have a electrode surface very low catalytically active, how we can improve? So, we need enhancement, so that we can improve the electron transfer rate very high. So, we want to shift your cyclic voltammogram peak from right to left. This is called improvement or enhancement. Clear? So, in this slide, so basically this is a very fundamental theory to understand your electrocatalytic activity of your sensor surface by measuring a cyclic voltammogram of a substrate. This substrate basically should be irreversible phenomena, it should show, then only you can easily predict your electrocatalytic activity, you can easily predict. See, if it is so the left side in this region high current, then highly active, very right side is low active, in between medium active, and if you want to shift from right to left, then you have to improve. So, you can see the cycle generally if your surface is totally nanoparticle coated, so you may get this kind of cyclic voltammogram. Okay. So, let us remove so these things, and now if you have this kind of cyclic voltammogram, how you may get? So let us come from this, if you think this one 1, this one 2 and this one 3. So, these 2 you are getting because of deactivations, right. Now, because maybe your nanomaterial somehow is coated something other material, some other organic stuff. Maybe you immobilize your nanomaterial with some protein layer that I taught you now in the last class, that if you measure the ferrocyanide cyclic voltammogram, if it is just like a bare surface, it will be like this. Now if it is the like your antibody coated, like, so it will be shifted, like it will be shifted little bit right side, oxidation peak, and reduction peak also will be shifted little bit left side, right, because some organic stuff already coated on your surface, because they are electrically non-conductive, they are hindering the electron transfer rate. So it is this kind of thing. Now if you can add some chemical, or maybe if you can improve this nanomaterial catalytic activity, then again it can be shifted to like the similar kind of cyclic voltammetry. So let us show you how we can improve. So enhancement can be done very easily, just adding a simple chemical is called NaBH4, that is sodium borohydride. So you have to make a solution of sodium borohydride, it may be 10 millimolar, and then you can dip your electrode inside this solution and just for 10 minutes, 15 minutes. See, you can see here this image. You can see, just think you are oxidizing hydrogen peroxide on your electrode surface. On your electrode surface, you just at the very beginning, before the any kind of treatment, you want to oxidize hydrogen peroxide, H2O2. Electron, it will be, so H2O plus O2, right. So in this case, when hydrogen peroxide decompose on your electrode surface, maybe you are getting in the first curve, this one, number 1. See, in this case, you are almost not getting the peak, and you are getting very low current also, and it is, if you stop your cyclic voltammetry, then you can see almost around 0.6, still you are not getting much good, a very good peak you are not getting, and current also very low. It means your surface is very low, electrocatalytically active. Now you dipped your electrode, so what you can do? So you can make a sodium borohydride solution, NaBH4 solution, suppose it is 10 millimolar, and you can dip for a 15 minutes. So if you dip it all your electrodes, then you can see this kind of behavior. You can see the oxidation peak actually improve. So in this area you are getting, and your current also, see, your current also increase in this. So if you see in this potential how much current you are getting at the very beginning, get this much current, but after the activations you are getting this much current. So it means your electrical activity improved. So this is called the chemical treatment. Okay, chemical treatment. One very important treatment, and it is very simple method. Now you can ask, is any electrode can show this behavior? That I will come now. So it's depend. Some nanomaterial is showing very fast electrocatalytic improvement. Some nanomaterial can show slow improvement, and some cases maybe you may not see much improvement. So it's depend on nanomaterial to nanomaterial, surface to surface. That I will come now. Okay, this is one point. And second point, also we can enhance the electrocatalytic activity by thermally or electrochemically. Thermally means just increase the temperatures. Maybe you can increase the temperature of the electrode surface up to 100 degree or some more than this, you can increase the temperature, and your electrocatalytic activity also can be improved. And electrochemically means suppose you have the electrodes surface and you have, this is the working electrode, right, and definitely always you have to use 3 electrode system for the electrochemical measurement. Means in this case means one is working, one is the reference, and one is the counter electrode. Now if we suppose this is a potential window, negative, positive. Now in a suppose this one 0.5 molar sulfuric acid. In this sulfuric acid medium, if you potentially scan, like many times, around suppose 20 times you scan, this is called electrochemically we are enhancing the catalytic activity. So, your electrode surface we are scanning around like 20 times or 50 times in a certain potential window, then also your electrocatalytic activity of your sensor surface can be improved, and that you have to do just before modification of the protein, otherwise it can be damaged because of the sulfuric acid and potential scan. So, definitely before immobilization of your nanomaterial, or after means some nanomaterial if it is very stable on the surface, that you can do, or before immobilization your protein stuff, you can go for this kind of this is called pre-treatment actually. This process called pre-treatment, means before just protein immobilization you can go this kind of treatment, so that you can enhance the catalytic activity. Okay. And also during this pre-treatment process on your electrode surface, if you have any impurities, they also can be removed, they also can be eliminated from the surface. So, kind of pre-treatment process is eliminating the impurities and improving the electrocatalytic activities. So, some cases you may not see much change of the impurities, but still electrocatalytic activity can be changed. By the sodium borohydride treatment, you can see the electrocatalytic activity change just dipping it 15 minutes, although not much impurities may be removing from the surface. That is the different reason. That reason I will describe after few slides. So, just try to understand that we can improve the electrocatalytic activity by different method. One is the thermal method, one is the electrochemical method, and one is the chemical method. So, thermal method by changing the temperature, electrochemical means by using some potential cycle, few scan you can try, and another is chemical. Chemical means just dipping your electrode inside a chemical solution. For example, I told you sodium borohydride, but slowly I will come different chemical, different thermal, different electrochemical treatment I will show you. So, you can see here one example, like just like the sodium borohydride treatment, you can see just a cyclic voltammogram here just before the sodium borohydride treatment, and after the sodium borohydride treatment you see the cyclic voltammogram is improved, is a big improvement you can see. This is because of chemical treatment or sodium borohydride treatment. So, how we can say that yes, this improvement already done because of this treatment? You can measure. First is the potential, you can see here potential here when it is oxidizing, and in this case it is oxidizing the higher potential. So, lower potential it is oxidizing means your electrode already improved its catalytic activity, and current you can see in this case you are getting this much current, and in this case after the treatment you are getting this much current. So, here I actually we are showing a example here. See your indium tin oxide coated electrode surface that modified with a dendrimer, just a linker that help to modify your surface with antibody or other stuff like nanomaterial. This is actually linker that will help for binding the other molecules or other substrate like the antibody, these things. So, here we modified with dendrimer with the DNA coated gold nanoparticle. Your gold nanoparticle already coated DNA, and this dendrimer actually helping to bind the gold nanoparticle on the surface. Now, this is your working surface, right. So, you can measure like a hydrogen peroxide oxidations or glucose oxidations on this surface. So, suppose on your electrode surface it is gold nanoparticle modified with dendrimer. Now, before treatment you can measure the glucose oxidations and measure the electron transfer rate, glucose oxidation, and after sodium borohydride treatment then again measure these glucose oxidations. Then you can compare, then you can see this kind of two cyclic voltammogram, one is the before and second is the after. Like this way you can easily mention yes, electrocatalytic activity actually improved. Okay. Now comes to the main schematic. of the enhancement, and let us try to understand the mechanism why this enhancement happen after the sodium borohydride treatment. So, this is a fundamental theory of the nanomaterial case. They can improve the electrocatalytic activity by different kind of chemical treatment, but if you try to understand the mechanism, what happen on the electrode surface and what happens actually on the nanomaterial surface by the sodium borohydride treatment, so that their electrocatalytic improvement is too fast. If you go back, see, just before treatment is this much, after treatment is enhanced is quite large. Why? So, for example, in this scheme I am just showing you that NH2NH2, this is called hydrogen. Hydrogen is similar like a glucose or hydrogen peroxide, just a substrate. This is just a substrate like the glucose or hydrogen peroxide. See, on the ITO surface, on the bare ITO surface, we modified the gold. Then we tried to measure the electrocatalytic activity just by cyclic voltammogram. So, if you measure the hydrogen electrocatalytic activity, something like this, you may see. So, this is negative, this is positive again. So, we are scanning from negative side to positive side, and this is the forward scan, then here stop, then this is the backward scan, right. So, if you see you can see the peak current here, and this is the peak current and this is the peak potential, very low. It means we can say that electrocatalytic reaction is very, very slow. Okay. Now, what we will do? We will do the sodium borohydride treatment. Now, after the sodium borohydride treatment, what happened? You know, the NaBH4 actually it can decompose in the aqueous solution, and it will generate lots of atomic hydrogen. Those atomic hydrogen actually, and this lifetime is very short. If it keeps the long time in the solution, then they will form the hydrogen gas. They will be removed from the solution. So, means immediately contact in the sodium borohydride solution, the hydrogen atoms, they will adsorb on the just outer surface of the nanoparticle, and there will be a surface reconstruction, this phenomena. Because of surface reconstruction, they may feel a strain and its electrocatalytic activity will be improved. Okay. So, this is the reason why electrocatalytic activity improved after the sodium borohydride treatment. So, if you dip this one any other chemical, maybe we may not see this kind of improvement, maybe other reducing agent. Sodium borohydride is a reducing agent, but in this case it is generating atomic hydrogen. In this case we are getting the improvement, but why not other reducing agent? Because in this kind of phenomena we may not observe, that is why. So, this enhanced activity again it can decrease, because this hydrogen if you removed, then again because of surface reconstruction, this surface activity again will decrease. So, this is just a assumptions, that is we thought that because of this it has happened, again this activity can be again slow, this enhanced activity can be again slow if it is hydrogen can be removed. So, after sodium borohydride reactions, this can be very fast, and if you deactivate it, mean if you remove it, then you can come again to the first stage. Okay. So, like this way we can explain why sodium borohydride actually can improve the electrocatalytic activity, and how we can again come back to the deactivated stage. As I said that you may need again the sometime lower electrocatalytic activity. So, then you have to remove this all the hydrogen. How we can remove the hydrogen, that I will come again. I will come this stage after some slides. Okay. See, so here you can see that here is the nanoparticle. Because of the catalytic hydrolysis of sodium borohydride, that atomic hydrogen is adsorbed on the surface, the hydrogen is adsorbing on the surface, and you are getting a surface of the gold nanoparticle, that is very highly catalytically active, and this phenomena is called surface reconstruction. You can see here mechanism. You can see that this is the metal, nanomaterial, and sodium borohydride means NaBH4 is the Na plus BH4 minus. See, so this BH4 minus, you can see they can adsorb, and this hydrogen atom may adsorb on the nanomaterial surface. See, and hydrogen also can be, they can come out from the surface as a gas. So, this is another phenomena I am now going to tell you. See, if you keep the sodium borohydride for a long time in acidic solutions, this decompositions, or this is called the self hydrolysis of sodium borohydride. It can happen rapidly if the solution's acidity is very low, means solution pH is very low. If the solution is acidic, if solution pH is very low or acidic, then these decompositions from sodium borohydride to hydrogen will be very fast. So, you may get very low number of atomic hydrogen on your nanomaterial surface. Then for activations of your nanomaterial, you may need long time, or it may not be that much effective. So, pH is also very important. So, enhancement, that is called the first catalytic hydrolysis, then your that is called the self hydrolysis, that should be slow. Otherwise, it will, all the sodium borohydride can be decomposed and hydrogen can be released from the solution, and you will not get the effective enhancement. So, your self hydrolysis should be slow, and how you can you can make a slow high self hydrolysis by making the pH little high, not very low, not very high acidic. So, what this is for this up to this teaching, I just taught you that how we can improve the electrocatalytic activity by the chemical treatment, for example, sodium borohydride, and the reason or the mechanism of the sodium borohydride, and they improve the electrocatalytic activity. That mechanism I taught you. So, this is a very simple process, and you may need only very few time, like only 15 minutes. In the next class, I will tell you that this improvement again can be further improved. Maybe we can decrease this incubation time. I mean, less than 15 minutes also we can improve the electrocatalytic activity. So, in this case, we can modify the sensor surface in some other nanomaterial, or maybe changing the pH, just now I mentioned, no? If we can avoid the self hydrolysis of the sodium borohydride, then also we can improve some different way the electrocatalytic activity. So, some other mechanism also I will teach you in the next class. So, that is all. Thank you very much for your attention.